So let's go back to rainfall runoff modeling. I anticipated some concepts in my last lecture, and I just would like to remind you that rainfall runoff modeling is useful for us in order to be able to simulate synthetic river flow data, meaning to generate data to estimate water resources availability when we don't have enough direct observations. So basically the problem arises when we have to take water from a river, for instance, or when we have to design an artificial reservoir which aims to regulate the flows of the river, and we actually don't know how much water is flowing into the river because we don't have enough observations. And this is a very common situation in the practical design because measurement stations are located only on a few rivers, but the great majority of the rivers, not only in Italy but all over the world, are ungauged. The terminology is ungauged, which means not gauged, not subjected to monitoring. And therefore the question is how much water does it pass across this river, and if we are not able to reconstruct this estimate from observations, of course we have to use an indirect estimation procedure, and one way is to generate synthetic data. And I already mentioned to you that the generation of synthetic data can be done by using observed rainfall or generated rainfall. The aim is the same, to reconstruct river flow data. If we have enough rainfall observation, we can use rainfall data to feed the rainfall runoff models. If we don't have rainfall observation, we just generate the rainfall as well. Now, as I said, we have to establish some governing principles. We have to write some mathematical relationship to build this model, this rainfall runoff model. And this mathematical relationship should be based on some governing principles. And I said that we are talking about fluid mechanics, we are talking about movement of water, and therefore we can say that the conservation of mass and energy are always satisfied in this problem, in this kind of problems, as well as the Newton laws. I'm not much concerned in Newton laws, but I'm very much concerned in conservation of mass and energy, because indeed this suggests us what kind of relationships we can use in rainfall runoff modeling. And the first relationship that we can use are indeed conservation of mass, which is very intuitive, conservation of the mass of water, and conservation of energy. And it's intuitive as well, because we are talking about water that moves, and again, in any movement, in mechanics, conservation of energy is satisfied. So these are the basic principles that we should apply to build these models. And conservation of mass is the most intuitive by far, because it's clear that it's a water balance that we have to draw. It's a water balance that we have to compute. Through the rainfall data, either observed or synthetic, we have an idea of the income of water into our control volume, which typically is the river basin, the watershed. And I defined already what I mean with watershed or catchment or river basin. These terms are synonyms. So, based on the rainfall data, you have an idea of the input into the basin. If I were able to quantify all the outputs, the problem is solved, because the river flow across a given cross-section is one of the output, and it's the relevant variable for me. So the issue is to be able to measure the input, rainfall, and I assume that I have rainfall observation, and the issue also in water balance is to be able to quantify all the other outputs, because the river flow is not the only output. There are other outputs like evaporation, like deep infiltration, which means that there is a part of rainfall that falls over the watershed that infiltrates in the deep earth, and I can't find that water back in the river. that water goes, for instance, to the oceans independently of the river. So the issue is to be able to quantify these outputs. But it's very intuitive that if we were able to draw this water balance, we solve the problem. In this water balance can enter some state variables, like the volume of water that is stored in the basin, which are additional unknowns. I already treated this problem, I already mentioned this problem to you. In order to draw the water balance, I may need to describe additional unknowns, like state variables. And therefore, the number of unknowns increases. It's not just the river flow, I have to estimate additional ones, and therefore I may need additional relationship. And for this reason, energy balance may come into play. What is relevant for us is to compute the water balance. But in order to be able to compute the water balance, in order to be able to describe the transfer of water, I may need to use additional balance relationships, like energy balance or momentum balance. It depends. So the basic concept is this balance equation, energy and mass are satisfied. The most intuitive requirements I need is to satisfy the mass balance, but to solve this relationship I may need also to use the energy balance. There is a problem that I already mentioned to you, which is, I'm sorry here the writing, it's a bit, let me delete this picture, like I did last time. There is a problem that I already mentioned to you, which is the heterogeneity of hydrological processes, which means just 1 second. Which means that these balance equations are valid at local scale, because the inputs to these equations are valid at local scale only. And let me clarify this issue that I anticipated last time. Think about rainfall, for instance. Rainfall is heterogeneous, meaning it's highly spatially variable. So it means that the rainfall input is varying point by point, location by location, into the catchment. So if we wanted to apply a balance equation at the catchment scale, we would need to estimate the average rainfall over the basin. We may take a decision. We may refer to average variables. This is a solution. In the presence of heterogeneity, a possible solution, if I want to apply a balance equation at huge scale, at a large scale, a possible solution is to make reference to average values. And therefore I need to estimate the average rainfall over the catchment, with the result that all the state variables and the other unknowns are estimated as average values over the catchment, including the river flow, which is fine, because when I refer to a cross-river section, the river flow is the product of processes that take place over the catchment, so it's fine. The only problem is that, to compute the average values for some state variables, like, for instance, the water that is stored in the catchment, may be impossible because of the heterogeneity. And also to compute the rainfall at local scale may be impossible because of, to compute average rainfall over the catchment may be impossible because it's very much complicated to estimate rainfall as an average value. So an alternative decision is to apply this balance equation at local scale and then integrate the local contributions at the basin scale. So one possibility, if I have a catchment with a river, and I want to estimate the river flow here, is to consider the whole catchment as the control volume and apply the water balance at the catchment scale, as I said. And this is called lumped approach. To do so, as I said, I need to estimate average values. Another opportunity is to divide the catchment in sub-catchments. Many small areas where I apply the balance equations at local scale. It's clear that in this case, with this solution, I need more information, but it's also clear that the representation is more detailed because I can take heterogeneity into account. Of course, in doing so, I estimate the river flow at the closure of each subcatchment. And then I have to transfer this, to sum these individual contributions to the basin outlet. So this is a complication. There are two complications. One, I need more information. The second is to integrate all the contributions. This is called the spatially distributed approach. Which gives, of course, a more detailed representation. What changes is the control volume. In one case, the control volume is the catchment, the full catchment. In the other case, the control volume is given by each sub-catchment, and they have many control volumes. I am skipping this slide. I will talk on it tomorrow, okay, on the Reynolds transport theorem. This is an important theorem that we will use to derive our balance equation. I'm just skipping it to tomorrow because first I want to explain to you some practical examples. So, the catchment or watershed is our control volume, as I said, which may be considered in its entirety as a unique entity, or we may subdivide. How to estimate the limits of the catchment? How to identify the part of topographical of Earth's surface that is included in the catchment? First of all, we refer to a cross-river section, and then the question is, given a cross-river section, how can I estimate its catchment? This is the first problem that we have, and usually the catchment is estimated by following the drainage divide. What does it mean, drainage divide, which in Italian is called linea spartiacque? It means the divide is the line that identifies the division between hill slopes that belong to different catchment. Meaning that, let's assume, just for now, that water flows to the river by following the topographical surface. I said this is not true because also water flows toward the river by infiltrating in the soil. But let's assume for now that the topographical surface is impervious, there cannot be infiltration, and water flows through the river by following just the hill slopes, no infiltration. Then it's clear, for instance, let's consider two different catchments, two different rivers. It's clear that if you have a drop of rain that falls on this hill slope in this position, then this rain flows towards this river. The opposite on the other side, if you have a rain that falls here, a drop of rain that falls here, it flows towards the other river. And the line that dictates the divide between the two watersheds is the catchment divide. Because this line, which is the collection of all the points such that a drop that falls over them may, with equal probability, go into a catchment or the other, this line, again, which is given by the cluster of points, the group of points, such that rain has equal probability to flow in one catchment or the other, this line is called the divide, because it divides one catchment from its neighboring catchment. If we have a sufficiently detailed topographical map, it's relatively easy, starting from a given river cross-section, to follow the catchment divide. It's relatively easy. This is the classical way to estimate catchment surface. There is a problem which doesn't take into account what happens underground. Let's suppose, for instance, in this case, that we have an impervious layer of soil in this position. What does this mean? It means that if a drop falls here and a part of rainfall infiltrates, then this rainfall is conveyed to the neighboring catchment, not in its catchment, as identified by the topographical divide. So this is a problem because indeed the situation happens quite often. And you know, the amount of water that is conveyed in the neighboring catchment without us realizing it depends on the amount of infiltration. And infiltration varies depending also on the condition of saturation of the soil. If the soil is dry, we have a relevant infiltration. If the soil is humid, infiltration is lower. If the soil is saturated, we may have no infiltration. This means that the extension of the catchment for a cross-river section varies in time depending on the catchment conditions. And this is a really relevant problem if you think a bit to it. Because it means that a given cross-river section can have a small catchment in arid situations and a much bigger catchment in humid conditions. This is really a relevant problem, which is not easy to solve, and explains part of the uncertainty that we have in hydrology. For sure, part of the uncertainty I mentioned at the beginning of this course, and I will mention again in the future, is due to the fact that the catchment cannot be precisely identified and defined. And of course, if you make a geological analysis of the site, you can derive indication that allows you to understand if there are the conditions that makes a similar situation likely. So additional information helps us, but doesn't solve the problem of precisely estimating the extension of the catchment. Okay, let's suppose for now that we estimated the catchment by following the divide. This is the approach that is used in the professional practice. In the great majority of cases, of course, we try to get information to support this decision, but in the great majority of cases, we adopt this description. And then, let's consider that catchments, this is just a picture that I put there just to give you an idea. Catchments are very diverse. They have different forms and structures. And there is a huge variability in the form and structure of catchments. Of course, their forms depend on the extension of the catchment, depend on the geology, depend on the climate, because, you know, catchments are shaped by rainfall, by erosion, among the others. They are shaped by the tectonic activity, but ultimately they are shaped by rainfall, so they depend also on climate. And it is very much important that we try to understand, and modern hydrology insists much on this concept. It is very much important that we try to understand the relationship that may exist between the catchment behaviors, catchment forms, I use form as a synonym of behavior, and the river flow regime, because for sure there is a correlation. For sure, if you see a catchment with a lot of vegetation, a lot of woods, you expect a different reaction to the same rainfall with respect to a catchment where you don't have any vegetation. And of course, if you see a catchment that is impervious, impermeable, you expect a different reaction to rainfall with respect to a catchment that is permeable. Because, as I already told you, a catchment that is impermeable cannot store much water. It replies very quickly to rainfall because it cannot store much water. Instead, a catchment that is permeable or vegetated has the capability to store water, and this is a very important capability to mitigate the effect of rainfall extremes, because the response of the catchment to an extreme is slower, and I already showed you some behaviors of hydrographs which clearly indicated this relationship. Okay, this is a slide which is dedicated to watershed identification by following the divide through the contour lines. And now let's concentrate on rainfall runoff modeling by providing some first examples. And let's not forget that we are trying with the mathematical model to mimic the reality. So in the reality we have rainfall that forces a watershed producing a runoff. What we are trying to do is to reproduce with the mathematical model the same relationship. And in doing so there is some uncertainty. This is our aim. And this is a problem that has been studied by humans relatively recently. Humans didn't start to try to better understand this relationship in ancient times. They started about 150 years ago. And the practical aim is to start from a graph of rainfall over time, which is called the hydrograph, and to derive a graph of river flow over time, which is called the hydrograph. And you can see here an anticipation of a very important concept. The rainfall runoff relationship is modified by humans, which is, as I mentioned to you, only a recent concept that has been introduced. In the past, hydrologists mainly tried to reproduce the rainfall runoff modeling in pristine conditions. Now, rainfall runoff modeling is modified by humans, for instance, by building an artificial reservoir. And here, this picture shows to you what is the effect of building an artificial reservoir. which has the capability to store some water, and therefore has the capability to, you see, change the hydrograph in this way by limiting the peak flow under certain conditions. And here you have an example. Let's see this picture in detail. An example of an hydrograph, the red one, before urbanization. When humans urbanize the watershed, typically you have the same volume of water flowing in the river, but the response is more rapid, and therefore the peak flow is increased. The area below the hydrograph is unchanged, which is the volume of water, as you know already, because we talked of this issue last week. And then typically you must build a reservoir, yellow hydrograph, to store water in the reservoir, so mitigating the peak flow. So by urbanizing the watershed, humans induce a reduction of the water storage that the catchment is able to accumulate, and then they usually try to remedy by building artificial reservoirs to store water. So this is a clear example of how humans may modify the rainfall-runoff relationship. These are examples of input variables. We talk about rainfall-runoff models, but the input variables are not just rainfall. We need, for instance, temperature, if you want to estimate evaporation. Evaporation may be an important contribution to the rainfall-runoff modeling, to the water balance. And if we decided to take evaporation into account, we need temperature data. And also we may need data regarding the catchment behaviors, river network behaviors, because if we want to describe in detail what happens in the catchment, of course we need to know the soil properties, the geology of the catchment, the geometry of the river network, because the geometry of the river network is effective on the rainfall-runoff transformation. So depending on the model that we decide to use, we may need a lot of input information. And of course, we would like to provide a representation of the rainfall-runoff modeling as much detailed as possible. But in practice, sometimes it's advisable to use simple models, because you know, they are easier to apply, and sometimes we have to apply models very quickly. So it's more advisable for many reasons, including simplicity and easiness of application. It's advisable to use simple models. And if we use simple models, some of the inputs may be dropped. And the output is, of course, the most important is river flow, but we may also include evapotranspiration, we may also include design variables like water levels, for instance. Because water level may be more important than the river flow when we design levees, for instance, works to mitigate the effect of floods, etc. And then let me talk about the structure of the model. So if we have the possibility to use different models, characterized by different level of complexity, let's introduce a classification. And I already introduced one classification, lumped model versus spatially distributed model, where the spatially distributed model again divides the catchment in subcatchments in different ways. I didn't tell you how we can divide a catchment in subcatchment. There are different methods. For now, it's just enough for us to know that it can be done. So you see the first classification is lumped versus spatially distributed. And then there is a second classification which is very much important. The classification is black box versus conceptual versus physically based models. And let me say something more. What is a black box model? A black box model, which is an exact translation in Italian scatola nera, means that we aim to establish an input-output relationships by completely ignoring the physical mechanisms that underlie this relationship. So the relationship can be purely mathematical, with no physical basis, we completely forget the mechanism and just estimate a mathematical relationship. Why this? Because it may be more efficient. The alternative is to increase the complexity, because usually black box models are very simple. And this is the reason why they very frequently work, because they are simple. By forgetting the physical basis, we achieve simplicity. The alternative is to try to better describe the processes. And to better describe the processes means that, of course, we have to call physical basis into play. But physical basis can be called into play in a very simplified manner. And let me give you an example. There is a very famous Rainfall-Runoff model, which we will see in detail, which is called the linear reservoir. This model assimilates the river basin to a tank with some water into the tank and the level of water in the tank. The volume of water stored in the tank is indicated with the symbol W, and we assume that rainfall contributes to fill this tank, and the river flow comes out from a bottom discharge. This has some physical basis, because of course this is what happens in the catchment. In the catchment we have a rainfall forcing, we have some water stored in the catchment, and we have an output which is the river flow. So it has some similarity with what happens in the catchment, and therefore it's for sure a model with some physical basis. But you see that physical processes are represented in a very simplified way. This model, which may make use of conceptual schemes to emulate the physical processes, are called conceptual models. It means that you have some physical basis, but not much. If we increase the level of detail, it means that we try to move one step further from the conceptual model. We move one step further and describe the processes by increasing the physical basis. And then what we try to do is to apply the physical laws, like conservation of mass, conservation of energy, exactly. We try, I said, because it's impossible to apply them exactly. But we try to apply the physical laws exactly. To do so, we have to necessarily move to a representation at local scale, because if we want a realistic representation of heterogeneous processes, this means that we have to work at local scale, because otherwise we don't get a realistic representation. We get a representation that is valid on average only. And if we go very close to a good physical representation, we may say that we are using a physically based model. And keep in mind that very often physically based is a synonym of spatially distributed. In reality, they are two different terms, but you understand why they are considered by some people synonyms. Because if you want to use a physically based model, this model has to be spatially distributed. The opposite is not always necessary. You can use a spatially distributed model which is not physically based. But indeed, you may understand why some people treat these two terms as synonyms. And let's note that given the uncertainty and the very significant heterogeneity of hydrological processes, strictly speaking, it's impossible to adopt a fully physically based representation, because you should apply the equation at infinitesimal time scale, spatial scale, and time scale also, infinitesimal scales. Given the high heterogeneity of, for instance, soil properties, which means that if you work here, the soil has a water retention potential, a water storage potential. If you just move 10 centimeters away, it may change completely. So this means that if you want to write a balance equation in the water column, in the soil column, you have really to apply the equation at very local scale. And you would need measurements of soil properties at very local scale. You may easily understand that this is impossible. We cannot make prospection, we cannot make, we cannot monitor the soil properties at a so small spatial scale. We can take observations, we can monitor the soil properties locally, but we cannot every 10 centimeters